things to catch up on. One is, I know I made this announcement, but somebody's been using the hand snips for the sheet metal, and it's looking a little rough. Nick tells me, it'd be a lot of pizza. Nick tells me that the full sheet's like $400 or something. So we're not saying you're necessarily destroying this, because I mean you could clean it up when you're done. But like this little piece here, why'd that get left on? So if you take it over to the press, and at least the next guy in line gets a nice straight line from it. The other part is, I know, well, not all of you, but at least some of you are new. It's hard to cut like this, so at the very minimum, pull it out, draw your line, and cut it with a nice shears so that it doesn't look like that. So anyway, make sure you cut them at the shear. If there's extra pieces, so for instance, say you need a 12-inch piece, but you only need a 12 by 8, well, only do 8. But you can cut the whole section off and then just leave the extra piece either by the big ones or even behind, if you walk in, right, kind of behind, first thing in the right on the door. You can leave the pieces there for the next guy so he doesn't have to pull a big sheet. He can go, oh, that looks like about the right size. I can use that. So make sure you bring it over to the shear for the rest of your classes too. In Christina's class, hopefully she won't have to go over that with you. Wanted to do some fun LED amperage math just for the fun of it. So our LEDs, if we were to draw a battery, plus, minus, ground, and we're going to run this through a light emitting diode. I don't know why I went all the way around. If that's all we did, and I had a 12-volt battery, basically we have very little resistance in our wire, right? So if that's all we did, and we say we have in the whole circuit maybe a 1/2 ohm of resistance, theoretically we got 24 amps. If we did 12 divided by 0.5, and we're going to burn out our LED and our wires, probably the LED first. And it's not going to work. So we're having you guys put resistors in series with them, right? And that knocks down our amperage through our LED. So because in your position indicator lights, you're going to have a red light, a green light, and a white light. The kind of most common way that gets done in here is with that kind of configuration. And it makes sense because you can solder your LED right to the resistor and run with that, and it makes it look like a regular light bulb. But some of you said, why can't I just do this? And the answer is, that works. It saves a couple wires. If your resistor burns out, none of the lights work, but we're not planning on resistors burning out anyway, right? But if we play with the math a little bit, if we had a resistor for each that was rated at, I forget what we wrote on the table, but let's say 500 ohms, just for the sake of easy math. So if it's rated at 500 ohms, what's the amp draw we're going to have through each resistor? If we draw it up there, we're going to have 12 divided by 500. That's going to spit out, all right, 0.024 amps. So we'd have 0.024 amps through each of those lights, and that should be enough to light them up. If I should have wrote it in 3 times, 24 amp, 0.024 amp. So that's what it would have been. Total gives us that's going to be about 7.2, right? Total amperage through that thing. Well, if we hook it up this way, now we're going to have 0.024 amps through our resistor. Our LEDs are not really considered any resistance, so our total is going to be 0.024, and it splits 3 ways, so you'd end up dividing that by 3 to say, what do I have through each LED, and it's going to be 0.008 through each. So we're going to have 1/3 of the amp draw through each LED. Now, if you were to go look up the model number of that LED, which could be fun, they eventually should get you a, hey, what's the amp draw on this LED it's supposed to be? Like, what is it like to see? If you change it from 0.024 to 0.008 on your bench, you'll notice it gets dimmer on most of them, or you'd say brighter if we have more amp draw going through it. So how dim or how bright it is, and you can only go to a certain point before it burns itself out. But that is kind of the math. So if you were going to do it this way, you're probably going to want to change out that 500 ohm resistor with, now really super easy math would be, well, if we bump that to a third of the resistance, 125? 166 ohms. If I switch that to 166 ohm resistor, my math will end up, if his math was right, back over at 0.24 through each resistor, and they'll be the original brightness. So everybody's seen how the math works out and how that would work, and how we can basically run our math to change through each of our LEDs. Josh?
Is there anything wrong with putting them in series?
That's an interesting question. I don't 100% know the answer to that. If we did our resistor, and then did our LED, then our next LED, then our next LED, being LEDs, I believe they will still work fine. Being a simulated aircraft, that's not how we'd ever wire them in an air. We'd never have our lights, to my knowledge, in series, because they're all going out different ways.
So hypothetically, if we did that, we should undo that?
Not even hypothetically. If you did that, you should undo that on your board. You wouldn't, so for instance, that looks all cool on your board, but once you get to a big, whoa, I didn't draw that right. That's a weird aircraft. If you get to your big aircraft, let's make the nose pointier. If you get to your big aircraft, you're going to come out of the cockpit. To run them in series, you'd have to have a wire going out, and then a wire coming all the way over, and then a wire going all the way this way, and then ultimately you're going to go to ground. So you've got 2 times where you had to run 2 wires, where we would normally wire it. You're just going to run a wire out, and then the other side of the LED is going to go to ground, right? So that's half of, or the biggest reason you're never going to run them in series on the actual aircraft. So let's keep them in parallel so it makes sense, but because they're LEDs, you could theoretically do it that way. The other problem, if you put them in series, functionally, what's going to be our problem flying our aircraft? Anybody?
One goes out,
Yeah, if one of the bulbs goes out, then they all go out. And we wouldn't want that. I'd rather just be missing one wing instead of all my lights. I mean, practically it still grounds me, but if I'm in the air, I'd rather be a little bit visible than not visible at all. Okay. Your midterm tomorrow, which I'm up to 4 or 5 people that are not taking it now. I think they're chicken. No, just kidding. It's you guys got writtens and stuff like that. If you're not taking it, just don't talk to your friends about what's on it. It's not that big of a secret. It's mostly just what we've been going over. So on there, it's 16 questions, but a good amount of them are drag and drop into the box. So it's 74 points. Now part of that was a handful of them have what I would call easy drag and drops, where I was just trying to boost your points, like boost your score, give you some gimme questions. Some of them should be fairly easy. If I was going to study much, I'd look over the PowerPoints, but basically just make sure you're paying attention in class. Now, I did, actually that's the next slide, sorry, I should blank that out. There are some questions on wire bend radius. So that one, I'm going to use the word you'd want it memorized. You could probably use process of elimination to figure out what number goes where. But for review, if I just have a wire out in the middle of nowhere, inside of there to fit the inside. What would be the radius, the minimum radius of that circle? Anybody got that one memorized? It's rolling around here. So it starts out with 10 times the diameter. If I'm not supported, if it's just around, 10 is the generic they use. So if we've got a bundle of wires, they're gonna go with whatever is the largest wire. They don't want that bundle bent any tighter than 10 times the radius of the largest wire in the bundle. So if you're looking at what's the biggest, 10 is generally our number. And then we start going, well, you know, if you had a bundle and you've got another bundle coming out of it and it's going to head somewhere else, maybe I should have drawn it all the way around back. If we're doing one of those, they're saying, well, that's basically, and this is going to be clamped, that's supported, so we'll get you down to 6 times if it's what they call reversing bundle. And they say, well, let's say we have just one individual wire and it's going somewhere, and I've got it supported here and I've got it supported here. So there's my terminal and there's where else. So this is the tightest radius that we ever want to see. What's the smallest number we'll ever see? 3. Yeah. So you got 3x on if it's supported. So if you remember those ones, those are the big 3, and you'll be good. I don't believe on this midterm I have the coax, even supported. I'd have to relook up the number, AC43 or something. It might be, I want to say it's down to 6 is minimum. But if you remember these are the big ones that you're going to want to know for the midterm. And pretty easy, right?
Are they all radius?
Yeah. I do ask.
Okay, then you're right. What does diameter mean?
Oh, so it's the radius, and that's the tricky part. Good question. So the radius of the circle in there can be 10 times the diameter of the wire. So you're going to measure the wire. Let's say our wire measures 0.1 inches. So if that's my diameter, so on the 10 times, you'd take that 0.1, multiply it by 10, and you'd say, okay, so that's going to give me 1 inch, but it's 1 inch radius. So if I said, how big of a can were you going to put in there, you'd actually say, I could put a 2-inch can if we're talking diameter of the can. So there is that, because we switch around with radiuses and diameters. That does show up on the question to make sure you understand that the bend radius, we're talking radius, but it's a multiple of the diameter of the wire, and the diameter is the full length, where the radius is just the half length, right? So it's making sure you get that radius diameter term.
What's the difference between the 10-inch or, yeah?
The 10, 10 is just a non-supported wire somewhere.
So the 6 is a bundle that is supported.
Yeah, basically 6 is, you've got one big bundle running and you got a couple wires coming out of that thing. They say, you know what, we're not gonna make you stay with 10. We're gonna let you turn that bundle back and go somewhere.
Would they need to be supported to get a 6?
Let's see, I'd have to go read it. Because it's in a bundle, there's kind of a, like it's supported with each other is kind of how they're going with that.
So the general idea is more or less a smaller bundle coming out of the larger bundle.
Exactly.
Okay.
Yep. Yep. All right. Let me erase that stuff. Making sense? Questions there? Other than that, there's questions like, you know, what part of a generator is the armature versus the field? The commutator, what does a commutator do? Stuff like that that we've been going over for quite a long time. So hopefully you guys are good with those kind of terms. Okay. general, is the way the lab worked out. So there's 2 of them working, I don't think Dean's got the last one working. Should be pretty easy for you. It's basically a repeat of the general lab, it's just it asks you different fault switches. So when you get a chance, you're welcome to grab those out and troubleshoot them. All right, when I did this lecture, I told y'all if any one wire is nicked or broken, it's bad. And then I was doing my studying and I was like, wait a minute, I gotta back that up. Because they give you a little bit of wiggle room. So I'm gonna back you up into the wiggle room. And the wiggle room is this chart out of AC 4313. And they say, okay, start counting strands. I'm like, what? So down here are, they call that aught, 0 to 00. They're like, there might be 1,000 strands in that thing. I'm like, oh, wow, I hope I don't have to count to 1,000 to make sure I have that wire. But their point is, out of 1,000 strands, they'll allow you to have 6 nicked and or, kind of weird how it reads. Is it nicked and 6 broken? 6 nicked or 6 broken? It reads kind of like and, right? But out of 1,000, you only get 6. So the reality is, you gotta be kind of careful. They're not giving you a lot of margin there. But our wires are gonna generally be up in this 10 to 12, even on our big wires, right? That's a pretty big wire for our small aircraft that we're running. 37 strands are pretty common. They'll give you up to 4 nicked, but no broken ones. So if we go back to this, you'd have to count pretty close. Hard to tell. This has way more than 4 nicked. So you'd have to individually count and go with 4 nicked ones. This one, I don't have as many strands in here, so it's not the right wire, because I have 1, 2, 3 nicked ones at least. Oops, wrong way. 3 nicked ones, but it's supposed to have 37 conductors if I had. So with 3 out of that, we're gonna be like, nope, I'm not gonna pass it either. Most of the wires you're using are gonna fall in this range, and they're saying 2 nicked, no broken. So that's back to essentially what I was saying, where out of 37, so a wire that looks like this, if you have even 3 of them that are nicked, so if you go beyond this, if you got 3 nicked ones, it's a bad connection, cut the wire, redo it. So I was within a hair's breadth, but I was technically wrong to say if you nick even 1, it's bad. You can nick 2 out of 39, but as you're stripping the wires, being careful, yeah. So when you're doing an inspection, for instance, if we get where you're like inspecting a component and you're looking at the bend that's going into that connection, ooh, we shouldn't really have bends that close to the connections, they should be straight in. But when you're looking at the connections, you start seeing nicked wires in those connections, and you go, well, I can go back to AC 43, I can go to table 11.13, and not that I'm wanting to condemn everything, it's just, oh, I see 3 nicked wires, that's more than this table gives me, I gotta put a new connection on there to make it airworthy. Make sense? I added this back into, I think it was lecture 7, so it would pop up, but I just brought it up today. If you want, in your books, you can obviously look at it yourself and find it. It's kind of buried in the electrical section. So, little correction, or maybe I would say deeper dive on that one. All right. Oh, one last thing on the exam. I don't think it would trip you up, but the lacing that we're doing, what do you figure the lacing is made out of? Oh, there we go. I didn't walk far enough. I think this is made out of plastic. Plastic is a generic term.
Synthetic.
So, the written question question, and what you'll see is it's typically made out of Nomex, nylon, or waxed linen. It gives you a couple things. I don't even know what Nomex is. Somebody would have to like.
Fire resistant.
Fire resistant? That would totally make sense. So Nomex, nylon, or waxed linen. So there'll be a question on there that talks about cable ties that are plastic and lacing, which is typically made out of Nomex, nylon, waxed linen. But wanted to point that one out. You would have probably figured that out. I did have it on my slide, the first slide where we talked about that, but you know, when we're rolling through stuff, it goes pretty quick. So just wanted to point that one out to give you one extra little point on the exam as a gimme. Cool. All right, we get to do capacitors. We briefly talked about this thing in general. How many of you guys feel confident where if I said, hey, come check my capacitor for class, where you could walk up here and be like, I can knock that out? Okay, so it was, yeah, we barely did that. Okay, cool. Just checking, in my head, you've done it 3 times already, because I prepped you to do this in this class, so I'm like, how far did we go? So we're gonna learn how to use this tool today. We are going to use it on small capacitors. You can use them on larger capacitors. You can use them on tiny little itty bitty capacitors, like this one. Why would I say this is a tiny little itty bitty capacitor? Anybody know? Yeah, it's got a very small capacitance. This is a fuel sensor. It's a capacitance style fuel sensor. We're gonna go over those coming up in a couple days. I'm not gonna take the time to look when it is, but basically it's a tube inside a tube with a wire connected to each one, and the fuel will go in between them. So if there's no fuel, it's using air as a dielectric. And is air a good dielectric? Not really. Is fuel a good dielectric? Not really, but it's better than air. So as it fills up, the amount of capacitance in this thing changes. So this is a little tiny capacitor. The interesting part with this one, and we'll go over it in class, is on our capacitor checkers, a lot of these have wires where you just clip them into the box to check. And wires run next to each other like this have a capacitance rating. We've got a wire in proximity to another wire. There's a word we use, we went over, that talks about, there we go, crosstalk. So if I actually, it was messing with me, if I plug this into the box and check my little itty bitty capacitor, it's gonna give me the wrong number, because this thing has almost as much capacitance as this thing does. So that's kind of wild, right? So that's how small of a capacitor this is. We're talking picofarads, I believe. So if you ever get to check in your fuel sensors, get a super sensitive one. What I did is I split the wires so they're not running next to each other, because there are, oh man, this should be memorized, 3 or 4 things that make a capacitor a good capacitor. One is the area of the plates, right? The second one is the distance between the plates, and when these are just loose on the table, there's a lot of distance, so that ruins the capacitance. And the next one is the dielectric material, and in air that far away, yeah, those separated ones, terrible capacitor. So normally though, you're gonna use these, but when we get into that class in a couple weeks, couple days, excuse me, it'll be fun. We're gonna fill up a jar with mineral spirits, and we're gonna actually dunk it in there and watch the capacitance change. How fun is that? So today we're gonna go over how to use this thing. I put EICO, I think that's how you'd say that, EICO 950 in yellow and red, because there's a decent chance you have to measure a capacitor for practicals. So you're gonna wanna know how to use this thing. And on the written tests, that specific number pops up, because they'll be like, if you're checking a capacitor with a, and I don't know if they're gonna change it or not, this is an old box. If I switch my view around, you got writtens and stuff, you might see reference to this specific box. It was the old standard for checking our capacitors. Any of you guys like rolling through writtens yet? Practicing, I mean, prepware? Has that popped up? Have you noticed? What in the world is one of those? The two that'll jump out at you is, they'll sometimes give a model number, but they'll say a mega ohm tester, or a mega ohm, depends how they phrase it. That's gonna be like that, similar to that yellow box we did, except it tests very high ohms. That yellow box is a pico ohm, or it's a tiny ohm tester. Alright, so rolling through, we can do it with that, or we can use my $100 one. If you got a good one like this, that can do the trick as well. The problem is, with my little $100 one, I can't test what we would call the breakdown voltage. This is gonna tell me what the capacitance is, but it's not gonna tell me how much voltage this can take before we fry it, before we start passing voltage in between the plates. I can do that with this guy, so that's kinda cool. The other thing is, this guy can be set way more sensitive than mine is. So this works pretty well for household motors, industrial motors, and even some electronics. But you get down to really small capacitors. If you get down to really small capacitors like these guys, or the other ones that are in this book that will show up on a capacitor lab, the electronic one that you have may or may not get that small because it's pretty tiny. Let me plug this thing in a minute. I'm plugged in. Okay. Switch screens on ya. And there they are. Gotta turn it on. We got a couple switches going on here. Voltage, I'm only gonna use for my breakdown voltage, and basically checking if my capacitor's bad. So normally we're gonna leave that one all the way turned down. There'll be another power plant with this, but we'll get you rolling now. This guy is my main selector for what I'm doing. Hard to read from where you're at, so that's probably why I have it on this screen. And that one, it'll give you microfarad ratings, and basically this small one down here is 10 mmF, so they actually call it microfarads, so 6 digits over, that'd make it a picofarad, right? So 10 picofarad to 5,000 picofarad, if I'm lined up on that one. And what happens is, on the chart here, it shows where you're at when you convert the scale by turning this. So you can find the spot where it says, okay, this is 10 mmF, and then the top side we said, oh, it's off the screen. The top side was 5,000 picofarad, so if I'm on the very outside number, you notice the numbers here, if I get all the way up to the top, I'm at 5,000 picofarad. So on the red ones, you gotta pick which one of the three numbers in line you're at, based on 1, 2, 3, 4 settings there. So it's actually 1, 2, 3, and let's find the fourth one. That one is 50 microfarad to 5,000 microfarad. So they're gonna take, the number that's actually on the chart, 50 up to 5,000. So you gotta watch really close what scale you're on. So that's what we're gonna adjust for, hey, what am I testing? Basically, when we're doing what we call the breakdown voltage, we're gonna go over to the paper mica test. There we are. So I spun that over. The glare is not ideal. Alright, I spun it down to paper mica test there. And when you see it in real life, you just have to trust me, I guess. So paper mica test is going to say, hey, what voltage do we start passing electrons through the capacitor at? So after I have it set to that, gonna turn my power factor and basically just click it to on. Over here, we're not using, so I'm just clicking it to on. You feel the detent go, and you see that cool green eye. If you're a Lord of the Rings fan, you'd be like, ooh, the eye of Sauron? What's Sauron?
It's like red.
Well, alright. So I'm gonna plug my leads in. We'll test this guy. Now breakdown voltage, this thing will send voltage through my capacitor. So if I turn it up past where it starts breaking down, I am sending, and I'm just wiring him in across there, I am sending power through the plates. Well, let's say the breakdown voltage of the capacitor I have is supposed to be 350 volts. If they say it's rated at 350, and my box here goes up to 500, I'm on the screen.
You said you were on the paper mic test with me here, it doesn't look.
Oh, you're right. There. How's that one? So it goes up to 500. So if I'm supposed to check the capacitor and make sure that we're good to 350, and I decide to crank my thing all the way up to 500, we're going to get one of two options. One is, it's good to 500. The other one is, turns out it's not good to 500. Now, it's not going to explode, hopefully. Maybe. But yeah, maybe I should put my glasses on. It's not going to explode per se, but it is going to send power through it, and what that means is we might leave some carbon trails behind. So theoretically, we just ruin that capacitor. So if I test it higher than what they wanted it tested at, I possibly ruin the capacitor. So you wouldn't ever want to do this on a capacitor you're using in real life. You would go to, maybe the magneto says, test it to 350 volts. You go, okay, I'm only going to go to 350. So I'm going to show you what happens when you go past, just so you get a good idea. But see the top right? See how it's mostly green? Whoa. Mostly green, but we got a little bit of a opening where it's not lit up there. As I turn my voltage up, basically what happens is when I'm turning, the eye closes. That eye closing is because I'm sending electricity into my capacitor. So if I give it a little bit higher voltage, trying to figure out how to get the screen right. If I give it a little higher voltage, I send more in. Well, a capacitor, after it gets charged, it goes, oh, I'm happy now, and it stops, right? So as I go up, I can see I get amperage going in, but once I take my finger off, it stops going in. So if I wanted to test to 350, basically I'm coming up, and when I get to 350, I want to see that it opens back up to the same amount, and I'm not flowing any electricity through my capacitor, so we know that the insulation's good, right? Now let's go up a little higher and see what happens. Whoa. And what we're going to get as we approach 500, and it's hard to tell, but notice it didn't really open all the way back up, did it? So we're trickling a little bit of voltage through that capacitor. It's still going, we got a little bit of voltage going through there. It didn't open back up to that full width like that. So this one does not test to 500. If they said test it to 500, you'd go, failed, this is no good. So if I wanted to know where it was, I could slowly go until I get to the point where I don't think it's opening. I think that's smaller right there. Wouldn't you agree? Which is better, A or B? A or B? I hate going to the eye doctor. I always think I'm going to get the exam wrong. I'm going to come out with these like big things. So I'm somewhere in the neighborhood of 400 volts when it stops opening all the way back up. So if they asked me, what is the breakdown voltage of this guy, I'd say 400. If they said, did you test it to 350 and it passed? I'd say yes. And if they said, did you ruin that capacitor because you went past 350, because you went past the breakdown voltage? I'd go, yes. Now I need a new capacitor. So the breakdown voltage part, does that make sense for everybody? So we got the voltage here, and when you get to where the eye stops opening back up is where you're exceeded the breakdown voltage. Some of them are just really good high quality capacitors, and you can't get there on here. On our aircraft, you don't want to go there.
So if breakdown voltage is past its capacitance, how are you gonna, do you ever test
It's
it?
past
to
its
find it?
voltage, not
Voltage,
past the
sorry.
capacitance.
But are you gonna try and find the breakdown, or you're just gonna be like?
Only in a
test it?
school setting.
Okay.
Or maybe you got a bad one and you're like, huh, I wonder how good these actually are. But no, on a part on an aircraft you're checking, you wouldn't want to go there because you're ruining it. It's kind of like saying, how much force do I got to do until this thing breaks? And you hear it snap and crack a little bit. Oh, that's it right there. Well, that's literally what's happening when we go out to, it won't open up all the way, is basically if it was a stick, it's kind of like, you heard it kind of cracking. And back to the issue there is, because we're passing electricity through the paper mica, the insulator, we might be leaving a little what we call carbon trail behind that the next time it goes up, electricity might go there. Now our capacitors, typically we're using them on like 600 hertz or 400 hertz or whatever the hertz are, right? So it's charge, discharge, charge, discharge. Well, I'm only doing this like once and I'm passing some electricity. Well, when I put it back in a system where the voltage is spiking and zzz really fast, if I have a little tiny carbon trail, it can build quickly once I'm back into the system because the power is going to want to go through that path. So anyway, so that's the one test. Now, if I had this thing all the way up at 400 volts and I was a little bit careless, guess how many volts are on those wires right now? Yeah, doggy. So just because I look like I'm not being careful, this is one test I'm not going to show you shorting myself. So I'm going to turn it all the way back down. Watch me do it eventually. But if you go back down to 0, I mean, you notice on the way back down, it actually goes, here, I'll go up. Watch it, and it should open, I think. Ready? Here we go, down, yep, it opens. So we actually had, our amperage was going back out of our capacitor. So once you go back down to 0, you theoretically should be able to, yeah, touch it. If I did that at 400, it would give me a pretty good
Turn it up to like 50, see if it works, cause we don't know.
Yeah.
So
25.
that's our paper mica test, and it's basically, it's just on down here. Oh good, it's warmed up. It's kind of a warm up thing. And you just spin your voltage up until it doesn't open anymore. All right.
The place you'd use that is just, you put it to the rated voltage to make
Yeah.
sure that it's actually opening. Is that how you would use, like,
So,
why you would test it?
yeah, if the rated voltage, does this one say what it is? A lot of times they won't even tell you. Part of the reason they won't even tell you is they don't want you to run over the box and be like, oh, it's rated at 350. Let me put it at 400. I just exceeded it. But yeah, that would be if a manual asks you to test the breakdown voltage. And that's why until I got to SMAT, I mean, I used capacitors all the time. Until I got here, I never checked the breakdown voltage because I don't want to go near there. I don't want to ruin the capacitor. But aviation, we can check things a little closer. So if they ask you to check the breakdown voltage, that's how you do it. That's the, I'm going to call it easier one because it's just on and up to where you're at, and it either passes or it doesn't pass. You really don't want to know where it doesn't pass because you ruined it. Let's take we'll make it a longer break, 8-minute break. We'll come back at 5:02 and we'll run through the other tests. If you want to come back up and see this in close up, you're happy to do that. Welcome to do that.
Why you use it, like, if you say, if they told you to test.
Yeah, so say you're doing an annual inspection on something, a component, let's say it's a magneto, they have a capacitor in them, and you've got a capacitor, and they say, we should have a 450 volt breakdown voltage. Make sure that it's still good. They'll say check it up to 450 volts. then you go over here, you go to 450, if it says, yup, we're good, you turn it back down and you say, yup, I'm good. If it had arcing on the inside, carbon trails, and it started getting weak to where, hey, it's rated at 450, but maybe it opens at 300, you go, oh, it's bad, we better replace it.
So you're not ruining it because you're not exceeding the break.
Yep, you're not ruining it if you don't exceed, but what happens
The dial
often
level.
is, boy, it's awful tempting to see, well, it's good at 300, I wonder how high I can go. And it does, visually, I mean, this thing's fine, right? So,
If you're just, once again, if it says 350,
Stop
you
at
test it there, and if the eye opens back up to where it was, you
Yep.
know you're good.
yep. I'm not 100% sure if it's gonna depend on the material or the quality as well. I've exceeded a lot of them in here, none of them have failed drastically. So I don't know if it's 1 out of 100, 1 out of 10, or if it's you did wreck it and it's just gonna take a year for it, that carbon trail to get bigger and bigger and bigger.
Yeah.
So,
Just don't exceed it.
don't exceed it. Alright, you wanna see that eye in person? In person. Here, we'll tip it up. Let you do it. Go ahead and turn that slowly, and you'll see the eye, yep. So if you go too slow, it barely moves, so give it 10 bumps and you see it close and see. So let's say it's 300, so roll it to 300. With the white line. Alright, it looks like it opened all the way back up to me. If you go all the way up. Yeah, it doesn't open all the way back up. Yeah, it's kind of fuzzy. At 300 it's very clear and distinguished. So I would say probably right in about there, where it starts to kind of fail. That's about 400. If you wanted to get really specific, you could, for instance, you could take a dry erase marker, mark on glass where it's at, but that's back to, we actually don't wanna know where it fails. We just wanna know that 350 is the number, we go 350, yep, looks good there, and turn it back on.
What does that mean?
That's what we're gonna do on the next test. Yep, different test. So this is the breakdown voltage test when we're set here on paper mica. We're gonna switch over to this test next. Yep. Yep. Yeah, it's just on, so off. So that first click is on. The rest of these are used for, I think it's a different test that I'm not using. So this'll do more than. Yeah, it's basically just on. Yep. Yep. Yeah, I would say where we have continual bleed. Yeah. It's actually, yeah, Dean would know more, but it's actually electrons being thrown out, and then they hit the outside and they light it up.
Like a code.
They call that an electron tube. Yeah, it's kind of like a light bulb, and when it gets hot, it emits electrons, and they fly out and hit the screen. Yeah, it's a little bit of both. I know enough to tell you that much. They're doing something with electrons. So yeah. Pretty cool meters. Okay, I'm gonna turn it down just so I don't drop it. Number 2? Yeah. I'll go check right now. Thought I had it up.
Almost there. I was saying that.
Does it? capacitor thing. I guess they're both capacitor tester things. Where we just wanna know the microfarads. So I'm gonna go the easy way. I'm gonna go to my meter, put it up here. You don't know how to work mine, because it's mine, not yours. But I gotta hit select a couple times. It says nanofarad or NF here, and I just gotta go across my capacitor, and it's gonna tell me 115.1. It does keep an N. Now I'm gonna admit, I don't trust my meter with scientific notation, so I'm like, because I don't usually measure those ones that small. But we'll write it up here. We'll see if this guy agrees. 115. It looks like a nanofarad. We'll see what happens. It's labeled as number 1. I don't know if they scratched it off. Your lab will have you checking them, and they purposely didn't label it. So, whenever you're checking these, one thing is you typically are going to want to start on the small scale, not the large scale. So I just clipped it in. I'm going to turn myself down to the small scale, kick it on in the same way. I got to wait for it to warm up. There we go. We got the eye back. Notice the eye is just all the way closed now, right? So when we're doing this test, we actually want to know what we're looking for is we're looking for the spot that it opens up and stays open. So I'm on the smallest one. I can roll around. There's a time delay in this world. There we go. Whoop, whoop. I'm getting to where it opened and stayed open, but I can't go past it. So I'm going to go one setting up and say, let's check the next one. And I go past. It went pretty quick, but did you see I go past it there? How it opens and closes? So we want to know, where is it the widest?
So what are we looking for?
I'd say right there.
I mean, like, what, are we measuring the capacity?
Yeah, we're measuring the actual capacitance of our capacitor. So, would you agree that I got it set at the widest right there? We're pretty close. So, now we've got to figure out what's the little black line on here. What's he pointed to? Because I'm on the second scale, which is hard for you guys to see, but it's 0.01 microfarad to 0.5 microfarad. This camera's not my favorite thing in the world. All right. 0.01 is the bottom or the inside of the 3 that are stacked up, right? And if I wanted to compare on the far side, I said it's 0.5 microfarad. Oh, that's interesting. It's actually, here, I can do this with a marker. Almost. I can almost do it with a marker. Man, oh man, there we go. All right, so I'm on the 0.01 to 0.5. So see how I'm on the middle number? So I'd be reading this number, and this number, and this number, and this number. All right, making sense? So if I go to my middle number, I'm at 0.1. So 0.1 microfarad. 0.1 microfarad. Hey, that's going to be probably correct if we transfer. If I was at 115 nanofarads, is a nano 3 digits over from a micro?
Micro's
I
nine.
think. So anyway, maybe 1, 2, yeah. So that's why I'm like, my meter, I don't know if I trust it. So 0.1 microfarad is what we're reading on our meter. That's where it stops. That's where we're opened up. Everybody tracking us on that one? All right, who wants to be our brave volunteer and measure this guy? Any volunteers? Want me to do it? I got to do it. Okay, I'll do it. All right, so I'm going to get rid of him. We said this was a tiny little guy, right? He looks big, but he's a little tiny dude. Oh, tiny little dude, and I hooked up my wires that have a reading all in themselves. So let's get wires that won't give us a false reading. One. Two. All right, I'm gonna go back to my smallest setting. Oh, way down there. So even on my smallest setting, we're pretty small. I would say,
How come it's got two?
are you seeing something up here, you mean?
Oh, it looked like it was closed
Yeah,
and
it's-
and open.
Oh, it might be because I'm going back and forth. So if I just do one swing, I'll do one swing all the way up. Open, and it's closing back down, and it'll stay closed. So I'm just going back and forth, trying to find the widest. I would say right about there. So if I line that up, hard to read again, but I'm at the 10 microfarad to 5,000 microfarad. So that's this one. And this is 50. So it's basically 50, 40, 30, 20, 10. So I'm at somewhere in the neighborhood of 27 or so microfarads, which I think is a pico. So, making sense? Everybody with me? All right, just for the fun of it, we'll do one last one that I don't even know what the number is. Those two I kind of cheated, already knew. We'll try this little guy. You think he's gonna be more or less than my fuel sensor? I don't know. I have no idea. All right, so we're on the smallest range. Ooh, could be way more. Oh, well, I'm off the scale. Back to the next one. Come on, give me a reading. There it is. All right. So I'm up at, if I'm looking at my second scale reading, the middle one, it's almost the exact same as what that guy was, 0.1. So, interesting, even though he's just a tiny little guy. It's about the same. Some of these small ones have a little bit different dielectric in them, a much better dielectric than what these are. So that might be what's going on. There's one thing Dean says, and I'm gonna admit, I don't actually know what he's talking about. There are certain capacitors that are polarity sensitive. I don't understand how that's even possible. Maybe get into it later. But there are certain ones that are polarity sensitive. I don't believe it comes up on any of your exams or your tests. I think that's an electronics thing. And Dean's an electronics guy. So if you're interested, you can ask him about that. But for us, we're just gonna get a reading. If you were measuring a goofy electronics capacitor and you couldn't get a reading, well, maybe reverse it.
Is there any way to damage it by doing that test there? Like if you went up to like pi scale and the highest setting, would that do anything, or would it just not give you a reading?
I think it just doesn't give you a reading.
That power factor,
I believe basically once you get what it can store, it's like, no, I'm full. I can't store anything else. So, yeah, it's not like the power factor one where we damage it. And part of that is if I'm on the correct one, part of getting my reading is I go past it here, right? So, yeah. Probably not advisable, but I don't think it's big. If you selected this one, you're like, huh, why can't I get a number? You're set too high. All right, cool. Questions on that? Good. Turn it off. Set it down. Get back to PowerPoint. All right. And erase the screen.
So your power factor knob,
Yeah.
a whole bunch
this thing a comparator as well. I think that's what you're using it for. And, it'll also do resistance, which I don't know how you do that either. I've got an ohm meter. These were the early version of, well, resistance checkers. Like, this is the really expensive early version of a good one of these. Now that I got one of these, I'm not carrying that out to the airplane. So it'll do more than, kind of like this will probably do more than I know. I'm like, I know how to work the ones that I need. All right. All right, we are going to shift gears. This is supposed to be kind of our, I'm going to call it systems lecture. We're in airframe. We're going to deal with systems through the rest of the year, right, in little bits and pieces. But this is supposed to be kind of looking at systems as a whole and being able to say, what's going on here? Where's the broken stuff? How do I know what's going on? So this particular one, I have to add a couple lines because I didn't write in quite copyright. So there's ground. That would go to my bus or my positive voltage. So once I finish that, basically we have a system here that tells us if our gear is down, the lights come on. Green light, green light, green light to say it's safe to land. If the gear is all up, all three are up, it'll just give you one light to say, hey, the gear is up. So that's what the system's designed for. It's a retractable gear aircraft. It'll also give you a warning. The horn goes off if basically the throttles are retarded. So I pull power on the aircraft, and the idea would be I'm coming into land and I pulled the power, but I never put my gear down. The aircraft will go, hey, you don't want to do that, because no matter how high you are, if you pull the power out, eventually you're going to land. So it'll start yelling and chirping at you. So pretty common is if you pull power, it'll be tied into some sort of warning or horn on aircraft with gear. That's what this horn does, is if the throttles are pulled, that horn goes off. And then the other gear warning visual, the red one, trying to remember, is I believe tied to the same thing. Did I give myself a note? I believe it is. We'll walk through. So it's always important to read it and say what's going on. So gear down and locked, indicator lights, and just because we're smart technicians, we can say, well, if the light is on, this would have to be over. So left, and on one like this, a lot of times I'll give myself a note and I'll say left is, and it's not necessarily up, but not down. Somewhere between down and up. It might be all the way up, it might be halfway up, but to the left is not down, is basically where they're at. And that's why in here, down and locked means we are definitely down and locked. Anything other than down and locked, those switches are going to show to the left-hand side. So if we run through and we say, hey, we're sitting on the ground, the gear is down and locked, we haven't taken off in our aircraft yet, we can follow our system through. We would say power can come in, and I can trace it down this wire, and oh yeah, look at that, right through the light. If my gear was down and locked, I could draw him over, and him over. So I'd be sitting there with 3 green lights showing down and locked. These ones don't close unless the gear is up, so that light would not be on. We'd say, hey, do I have power here? Let's see, power could come in through the flasher, and it's not going to get past these unless those are closed, but did I just say the throttle was out? So on this particular drawing, we could close those saying the throttle is out, and we would get a red, wait, hold up. So power's coming down, he's going through my flasher. If those were closed, power would be going through, and we would be getting a red light. Oh, I'm sorry, let me back up. this drawing's funny. This one, they all have a little bit of a funny thing. Ugh. Back to that, sorry. These close if my throttles are retarded. So we're saying my throttles are retarded, my engine's all the way back. Once those close, this guy gets power and he closes. Alright, so once he closes, I do have power across my horn, and that can come down. Erase this, and yeah, sure enough, my horn would be chirping at me. I don't know if I like this diagram. And the reason for that is on most of these, there's going to be a down lock squat switch that if the gear is down and squatted on it, it'll keep the horn from going off. This drawing doesn't give us that. So FAA didn't do us any favors. We found a situation where the horn would be sitting there screaming at us. That wouldn't be very fun, but it's possible. So they're going to use this though, and they're going to say, if your gear is up, you're flying, your gear is all the way up, when will the horn go off? So you'd go in here and draw, and you'd say, okay, my gear is up. We said that's to the left, that's to the left, that's to the left. That would allow the horn to go off if we close this. What closes those? My throttle switches. So if I'm flying along and I pull my throttle back, now my horn's going to go if the gear is up. If the gear's not up, that horn can't get ground through any of those paths, so the horn's just not going to go off if the gear's not, maybe up's not the right word, but not down. Not down. All right, this guy over here, they might say, when will the gear retracted light come on? And you'd go back to, well, all of my up switches would have to be closed. So if all three of my up switches are closed, I could follow power backwards, right? Oh, okay. If my gear is fully up, I'll get a green light for the up switches. So you could spend a half hour, 45 minutes on this, asking questions like that, and figuring out what's going on. But that's basically what they're going to ask you, just simple questions like that. They might say, these numbers aren't labeled right now, but they might say, if this wire here breaks, what's not going to function on our aircraft? Jars out, because we're going to be using them today. Okay, lead. If this wire were to break, what's not going to happen on our aircraft?
The relay would get close.
Yep, the relay wouldn't be able to close. The pilot's probably not going to hear the relay closing. What do we need the relay to do?
Power the left, right nose gear switches.
Well, switches don't get power, so they're only switches. What would actually eat up our voltage? Because the switch doesn't give you a light, it doesn't give you a noise, it doesn't do any work, it just turns stuff on and off. So you're in the right neighborhood, but as a pilot sitting in the cockpit, if that wire were to break, what am I going to notice doesn't work? So you are right, that coil is not going to get power ever, which means this contact's not going to close ever. And those are down to, it gives us a path to ground, but it's a path to ground from this guy and a path to ground from that guy. So as a pilot, my horn's never going to go off, and my gear warning visual is never going to work because that coil never closes to give those two loads. Those are where the voltage is going to drop, right? So the voltage will never be able to pass through those and get to ground. So those are the type of questions they might ask on a drawing like that. So we'll try another one. Let's say, the right gear switch either broke or got dirty, or somebody hit a deer and it's not working.
Switch doesn't work. I think that you got bigger issues.
Steven, what would the pilot potentially notice if this gear switch stopped working? Yeah, the right gear. So maybe he hit a deer on takeoff or landing the last time, and he puts his gear down, and he's coming in for a landing, and he's like, my gear's not down. Why is my gear not down? And hopefully they put in a push to test, so he can be like, is it the light bulb? Maybe it's just the light bulb. You hotshot pilots, the first thing you'll do is you'll push to test it, and if it still doesn't work, you'll pull this bulb out and you'll put it in there. Hopefully it's just the bulb. Because if it's more than the bulb, now we got issues, right? We're gonna do a gear up landing, and then land with a gear. But yeah, exactly. So those are the type of questions they'll ask is if a switch doesn't work. So this is a little bit easier one. We'll do one more. Let's say the left gear up switch doesn't function. Charlie, what's my pilot not gonna have telling him?
You're not gonna have your right or left gear switch right.
Say that again?
You're not gonna have your right gear or your left gear.
So here's my left gear, these.
And you say the switch is broken.
I said this switch here is broken.
Yeah. So you're not gonna get power then down through the other switch either. Down there.
Down here? You might have to draw that out. I don't think I'm following you.
Yeah. So if that switch is broken, you're not gonna have anything grounded there.
I'm not gonna have grounded here, yeah.
So that is it, the gear up.
Gear up. Yep.
That light's not gonna work.
There we go, okay. That was getting scary. The gear fully retracted indicator light won't work. So I take off and I'm expected to see my gear is up, but I never see that the gear is up. I'm like, oh man, did my landing gear system break? Do I got a gear leg that's kind of hanging down while I'm flying? I got problems going on.
What's the purpose of that resistor next to both those lights, you know,
Now, I think they might be giving you a goofy, like, push to test or something, but, yeah, shouldn't really be much going on there. Because, at least in the drawing they have, there's no load in between here and all the way down to the resistor. So, if the light has power, the resistor has power, it's not really anything. And we can get more complicated diagrams where maybe they got something going on, but yeah, in this instance, we don't know. You can ask a lot of questions that the answer is, we're not sure, they didn't give us that info. All right, what is this? Kind of hard to see, but you'll be able to read it. This is kind of a fun wiring diagram. First person to get it, shout it out.
It's a wiring diagram for skydiving signal light.
Skydiving signal light, man. We're trying to make life exciting for you so you don't fall asleep. So the pilot in this case, he's got all his dudes with parachutes in the back, those crazy people that jump out of planes. And he's got a door on the right-hand side of the aircraft and a door on the left-hand side of the aircraft. And he's going to tell them it's time to go. But instead of just that, a lot of times they'll put the aircraft in a slip one way or the other. And he wants to know, do you go out the right door or do I go out the left door? So he's got a little switch on the cockpit that can turn on a right door switch or a left door switch. So skydiving light, that's kind of cool. That way he doesn't have to yell, he can just be like, time to go out the right door. So that's what we got going here. If I used an old voltmeter, I say old voltmeter, the old style, if you're the kind of fellow that's like this style, and normally when we use these, we're going to clip this side to ground somewhere, right? We're going to say, hey, okay, I'm grounded on the aircraft. Do I got power? here, this is basically just saying it's the instrument bus. So if I put it on there, bing, I'd have a light bulb light up. And we go, yep, okay, I got power here at the bus, right? And here's a breaker, so if I go to the back side of the breaker, the light theoretically lights up. And I go, okay, I got power there. If I went to here and the light didn't light up, what would be my problem? Breaker's trip, yeah, okay. All right, so let's say I go out to this point, well, let's say the left light bulb is not lighting up. So the guy goes, he flips the switch to left, and the left light bulb doesn't come on. And so, hey, my left light bulb won't come on, they never jump out of the left side of my aircraft. Can you help me out? So you pull in and you grab this old style meter, and you go, huh, that's interesting. And you take your meter and you go to the wire that says left on the left light bulb switch, and it lights up. So this thing's all lit up. Did that tell us anything? Yes or no, or what did it tell us? Harrison. Oh, you got a tricky one. Yeah, I put my meter here, and my light bulb lights up on my meter. Does that tell me something? Still, he said still, I have power here. Okay, so what would you do next, or which direction do I go? Does that mean my light bulb's good, or my switch is good, or what would you do next? What? You check the switch by what, going to here? All right, if I go to here, now my light bulb does not light up. Lights up here, lights up here, lights up here, doesn't light up here. So what's our problem? Yeah, the switch isn't working. And that's why I've got this one out. You got to make sure when we're talking voltages and pressures, right? Where is it supposed to be? Normally, when this is working correctly, that switch is going to go to left. And if I were to go here, I'd be connected directly to ground and I wouldn't have a light bulb, right? Because the voltage would drop across my actual light bulb, and then it's just going to ground the rest of the way. So because I still had a voltage here, it's acting like the switch is just in its neutral or not closed position, and it's telling me that, must be the switch is defective and the switch isn't working. If I had a different style voltmeter and I wanted to check it, I could read across the switch, and if I had voltage across the switch, we'd go, yep, definitely a bad switch. You could otherwise, and that's basically what we did, right? We went from ground across the switch, the light bulb lit up, so, oh, bad switch. Leo?
Technically, if you would have done that the way you had it, you would have turned on the left light bulb too, right?
It's possible that the light bulb itself would have lit up because I might have had amperage going through mine, which is why I don't necessarily like these. But, you know, all right, so we're going to change the scenario, and the skydiving guy flicks the right light on, and the light's not coming on. So he grabs this guy, and he goes up to this point right here, and the light bulb, this light bulb does not light up. Man, this thing's not lighting up. Either what's that telling us, or what would you do next, Isaac? So no light here. Check my bulb, like pull it out and visually look at it. Sometimes they're hard to see, like a push to test, so I'm not going to let you do that. It looks fine to me. I don't know, I can't see anything wrong with it. Check the resistance of the bulb. You got me. All right, what else could you do if you're not Isaac Finney? Maybe the bulb's buried somewhere, Daniel. So I don't have power to here. He just went to the easy check the light bulb. Check the other side. Whoa, the light lights up. probably got a bad bulb. All right, what if I went over here, Isaac, and this thing did not light up?
Your test light,
Yeah.
probably check the fuse.
Yeah, check the fuse of the circuit breaker. So depending on how hard it was to get the light bulb out, I might have wasted a bunch of time. My breaker could have been tripped. So if I had the thing here and I'm checking here already, I can do this in about 2 seconds. It might take a little longer to get the bulb out. But just goes to show there's a lot of different ways that you can check it, and it's just what's gonna be more efficient. All right, so that one's fairly easy and straightforward. Everybody making sense, following us on an easy one? Cool. All right, the next one's where they start to get a little bit more fun. Flap switches. And you'll want to be familiar with flap switches. Highly unlikely you'll get a O's and P's question on flap switches. Highly likely, when you start working on aircraft, you'll have to work on flap switches. So the way they work is in the panel, you've got the little handle that the pilot moves. And what he's actually doing is he's rotating kind of a cam. You can see the cam there. See the cam here, see the cam there. And if everything is positioned normally, the flaps are not moving, everything is happy, I'm gonna say in a middle position, so 20 degrees of flaps. What happens is that cam is in between the two micro switch rollers. So neither of those switches is tripped or activated. They're in the normally open position. I was gonna look at the diagram. We'll make the diagram bigger in a minute, because they give a normally open, normally closed. But they're in the they're in the normal position. I'll put it that way. They're in the normal position. If I roll this guy, whether I wanna go flaps up or flaps down, when they cover one of the switches, then that switch will be not in the normal position. It'll be the opposite of the normal position, is how I want to phrase that. So what literally happens behind your panel is you move your selector, the motor moves out on the flap motor, the flaps move, it's tied to cables, and it actually moves this whole housing that holds these switches. That whole housing will move until now both my switches are in the happy place, and they go, hey, we don't need the flaps to move anymore. So it's a really wild system that way, in that you don't see it happening behind your panel, but if you go to go flaps down, that holder that's holding those switches actually rotates until neither of the switches are pushed again. So that's kind of weird. And then out in the wing, there's also, and it depends on the system, there's a lot of different wiring ways, but there's often an up limit switch, so that if the flaps get all the way up, instead of the little thing in the cockpit being what limits how far they go up, it's actually out in the wing that says, yup, we're all the way up. It's more accurate to get to the correct position. So they'll put it all the way up is out in the wing, and then same for down. All the way down is out in the wing. So if I go to put my selector all the way up, I'm going to turn the motor on, and it's going to go until it hits the up limit out in the wing, and it's going to shut off. But in the cockpit, we'll still be sitting on top of the up switch going, I want up, I want up. But out in the wing, it'll say, I'm not going to let you go up anymore because we don't want to break any cables or bend the wing or do that kind of stuff. So this is the most common version of what we got going. So little bit tricky to follow if you're not thinking slowly through it. When they draw them, it gets tricky because you say, okay, Mr. Guy Drawing, which position did you put me in right now? So if I'm looking at them, a lot of times, especially if I'm learning, I like to look at it and say, where are they going to be normally? So these ones, normally open, normally closed, okay. Closed, we're in the normal, so down limit, we're not sitting on the down limit. Up limit switch, normally open, wait a minute. I'm sitting on the normally open, but I'm closed. So this tells me in this configuration, I'm actually on the up limit out in the wing. Does that make sense? sense?
It says it up there.
Yep, so it's up limit switch.
Donna Visser.
Sorry, Mom. So I'm on my up limit out in the wing. So the flaps are all the way up. We're not sure where the selector is yet. We'll come over here and say, what's the selector asking for? Ooh, that's on normally open as well. So it's closed, but on the normally open. So in the cockpit, the pilot's got the selector all the way up. He's saying, I don't want any flaps, which means the switch in the cockpit is still on normally open. And this one out here is basically what's saying, okay, that's it. That's all the motor we're going to give you anymore. We're going to shut it off. So we can trace this through in that position. We would say power could come through that switch, but it gets back to here and it's not connected to anything that way. The other place it could have gone was this one, but it can't get through there. So both my routes for power to go end up in a dead end. We don't have any motors running, right? So that's how it's currently sitting. I would like to draw this in, I'm going to call it 20 degrees of flaps, just the happy medium position with nothing running. That helps us understand what's going on. So I want to put it at the normal position. So we're going to put him normally closed. This one's normally closed. I'm going to put him in the normally closed and him in the normally closed. That's supposed to mean it's not there. So with all those in the normal position, nothing should be running. So if I take my power, I can't go through that one, so he's coming up. He could go through here, and once he gets down to that terminal, he's not going anywhere. So I don't have anything running. Everybody with me so far? All right. So now let's say I go from 20 degrees of flaps, maybe I'm in the 206, and we're doing tight circles around the landing strip, trying to see, can I get in there? Is there a cow on the runway? Because that's what we do in the mission field. We set them to 20 degrees so we can fly slow. And we go, okay, it looks like it's good. I can land. So I get back out into my pattern, and I push my selector to flaps down. So I come out to the selector switch, and I'm going to close the flaps down. Well, now my power that runs out through my down limit switch comes back. Whoop, I can go through that flaps down switch, and I can come through my motor. Oh man, it's a long route. It's like a big race course. All the way back through the flaps up, over to ground. We used like every wire in the system, didn't we? But we ultimately got back to ground. Now, I got to do that again because I didn't remember which way I went through the motor. Does anybody remember which way I went through the motor?
Right to left.
I went right to left. Okay, right to left. So, this direction in conventional flow is going to be flaps down. If I have power going right to left, the motor will spin flaps down. With a DC motor, if I reverse my voltage, we're going to reverse the direction. So we said, okay, we're running flaps down. Now, there's one of two things that'll stop it, right? One thing is if the flaps make it all the way down, my down limit switch would switch over to here. And if we were to track it, my power had to go through that one to get there. So if it switched down to there, I don't have power, so my flaps stop moving. So we're like, okay. The other thing that could stop it is, let's say I set it to 30 degrees of flaps. So I put it to 30, it starts moving until it gets to its happy spot at 30 degrees. Neither switch is in a position anymore, which means my flaps down switch would go back to normally closed. And if that's on normally closed, if we were following it through, we'd get to here, and I can't go anywhere again. So the motor stops running. So pretty cool setup how they figured that out. So let's say I'm at 30 degrees now. I'm at 30 degrees of flaps, and a cow just ran out on the runway. Wait, this is American Aviation. A crocodile just swam. I've never seen one. The plane's too loud. A log. It's a log. There's a log in the river. I can't land, I gotta do a go around. So I power it up, I put the cowl flaps up, and then I wanna put the real flaps up. So I take my flap handle and I go all the way to 10 degrees of flaps. So that means I came over to my flaps up, and I put it to, I come over to my flaps up, I put it to not the normal, but hey, I want flaps up. Now if I follow it through, I'll go this way first just for the fun of it. If I take that wire, once I get back to here, I still can't do anything, right? So I go, okay, no power going through that one. Let's check the other route. Ooh, okay. I've got a path. Oh, I'm gonna be going the other direction, huh? I'm going the other direction through my motor now. And back to ground. So I got a complete circuit. So my motor is now running flaps up. And it's gonna keep doing that until it gets to 10. And this guy goes back, right? Once we get to 10, everything behind my panel will say, hey, I'm going back to normally. Now let's say I do it one more time. I go all the way to flaps all the way up. All right, so I go all the way to flaps all the way up. But once they hit my up limit switch says, hey, I'm all the higher I can go. The power can't get back across, so it can't come through and get back across, so the flaps go, we're gonna stop running again. All right, so that's your run through on a very simple flap system, if you can use the word for simple flap system. But you gotta kind of be like, okay, what's reversing? So if you had a call and they say, hey, my circuit breaker keeps tripping on my flaps. I go to flaps all the way up, and my circuit breaker keeps tripping. And it sounds a little bit funny before it trips. So, pop. What's a likely cause?
Limit switch.
What limit switch, Leo?
Were we going down or up?
Up. I was going up.
Up.
Yeah. My up limit switch might not trip. So basically, it's going to try to keep rolling those flaps all the way right through the wings. And the motor's not going to be able to handle it, and it might pop the limit switch. I had that on an aircraft I was flying last week where the up limit switch stopped working, and it started popping the breaker. That's a lot better than popping cables, because some of them, they'll actually, the motor's pretty strong, and it'll crank that cable right till it goes poing. Not a good idea. All right.
So what'd you do? I wanna know the story.
They diagnosed it to bad switch, and the mechanic, not me.
What'd you do like when you were flying? Like, how'd you know?
The breaker would trip. So the flaps were up, but then the breaker would trip, and you'd go to put the flaps down. Well, nothing happens, because now my breaker's tripped, I got no power. So he's doing no flap landing. And then we said, let's do a couple more no flap landings. Not sure if that's legal or not. Once you're down on the ground.
Got down.
I mean, the no flap landings are legal. You can fly it without it. We might have had to sticker it in up, technically, to go back out. But we stickered it in up. All right, let's do I'm going to say 7-minute break. We're going to keep it short. I got about 4 more wiring diagrams. We're going to take a little bit less time on them. And then we'll go to the lab. So come back at 10:02.
Did you decide on a color or?
Well, some of them were this, I'm gonna use the word repeat. So, I'll go to the end. So, that one and that one are the same thing. It's just one of them highlights the voltage, which is the same as that one. So it's one diagram. One diagram, just pointing out so I don't have to highlight it. So there's one. This one is basically the same system, they just switched the numbers around. That's that one and that one. So it's kind of 2.5, 3. So, depends how you look at it. Depends how you look at it. All right, what I'm gonna do, guys, is I'm gonna say we'll take the last half hour before Devos. So we'll let you wake up by doing actual work. And we'll say come back here at, is that clock right? 8:44. We'll say come back here at 9:20.
Then we have Devos is at
9:25. Yeah, Devos would be 10.
10. Then we still
Wait,
have
10:25. Yeah, sorry. 10. Let's make it 10:20 then. I'm gonna write it on the board. Yeah. The hour hand on that clock is wonky.
You need to get a digital one that syncs up with the scanner.
So supposedly that's an atomic clock, so it is synced with the scanner. It's just the hour hand. All right, so 10, 20.
Is that when we're supposed to come back?
Yeah. We'll see how it works. If it works out, I might like doing that to break up the lecture. Part of me is like, when you get working, you don't want to stop working and get, right? Like,
Yep, it's a nap time in the morning though.
yeah. I was watching, I had about 4 or 5 of you that are fading. And I'm like, if we do the wiring diagram,
Was I one of them?
it's just gonna go, you were in the fuzzy range.
Yeah, that's about right.
Yeah, yeah, yeah. I remember when I was sitting in here, especially like during a sermon, you do the whole, I can pay attention better if my eyes are closed. And I'm like,
That's a dangerous game.
yeah, but from up here, I'm like, okay, I'm losing them.
But close them for
Is
just a
he
little
out
bit too long
or is he
one time.
listening? Yeah,
Close them for a little bit too long one time, and they'll just out,
Yeah.
getting nothing.
yeah,
I'm just praying for you at that point.
yeah. Sometimes I'm doing the one eye, give that one a rest.
Hey Case, did you throw in a little Brian Regan joke about your eye doctor? Is that a Brian Regan joke?
I love Brian Regan, and I love that joke. I didn't throw that in yet, did I? In a PowerPoint?
Yeah,
And I didn't say it?
you were talking
Which one was it on?
about the whole eye clicking thing.
Oh, no, that wasn't a Brian Regan, that's just me. I hate going, which is better, 1 or 2? Does he talk about that piece?
Yeah.
Oh, I didn't know he does that one. He's got the LASIK one, which is, oh no, that's not Brian Regan. There's another guy, sorry, when you say I and then joke, my
Yeah.
brain really quickly runs to Don Friesen.
Okay, I've never heard
Oh my word.
of it.
Similar to Brian Regan, similar style comedy. The most hilarious